Welcome to Accelerated Chemistry. If all atoms are composed of the same subatomic particles, what makes the atoms of one element different from those of another? The answer is the number of these particles. The most important number to the identity of an atom is the number of protons in its nucleus. The number of protons defines the element. For example, an atom with 2 protons in its nucleus is a helium atom, and an atom with 6 protons in its nucleus is a carbon atom, and an atom with 92 protons in its nucleus is a uranium atom. The number of protons in an atom's nucleus is its atomic number and is given the symbol Z. The atomic numbers of known elements range from 1 to 116. Although evidence for the synthesis of additional elements is currently being considered, as shown in the periodic table of the elements. Each element identified by its unique atomic number is represented with a unique chemical symbol, a 1 or 2 letter abbreviation listed directly below its atomic number on the periodic table. The chemical symbol for helium is He, for carbon, C, for uranium, U. The chemical symbol and the atomic number always go together. If the atomic number is 2, the chemical symbol must be He. If the atomic number is 6, the chemical symbol must be C. This is another way of saying that the number of protons defines the element. All atoms of a given element have the same number of protons. However, they do not necessarily have the same number of neutrons. Since neutrons have nearly the same mass as protons, 1 AMU, this means that, contrary to what John Dalton originally proposed in his atomic theory, all atoms of a given element do not have the same mass. For example, all neon atoms contain 10 protons, but they may contain 10, 11, or 12 neutrons. All 3 types of neon atoms exist, and each has a slightly different mass. Atoms with the same number of protons but different number of neutrons are called isotopes. The sum of the number of neutrons and protons in an atom is its mass number, and we represent mass number with the symbol A. For neon, with 10 protons, the mass numbers of the 3 different naturally occurring isotopes are 20, 21, and 22, corresponding to 10, 11, and 12 neutrons, respectively. A nucleus is a collection of protons, positively charged, and neutrons, uncharged. We know that positively charged particles, such as protons, repel one another. So, what binds the nucleus together? A fundamental force of physics, known as the strong nuclear force, binds the nucleus together. All nucleons, that is, protons and neutrons, are attracted to one another by the strong force. However, the strong force acts only at very short distances. We can think of the stability of a nucleus as a balance between the repulsive electrostatic force among protons and the attractive strong nuclear force among all nucleons. The neutrons in a nucleus therefore play an important role in stabilizing the nucleus because they attract other nucleons through the strong nuclear force, but lack the repulsive force associated with positive charge. The activity emitted by these depends in part upon the ratio of neutrons to protons. Neutrons to protons that are too high will lie above the valley of stability and have too many neutrons and tend to convert neutrons to protons via beta decay. A neutron to proton ratio that is too low will lie below the valley of stability and have too many protons and tend to convert protons to neutrons via positron emission or electron capture. Provided in the chart are 5 forms of decays that we will discuss in class. Alpha decay is effectively the decay in which a helium nucleus is emitted. Beta decay, in which an electron, a high-energy electron, is emitted. Positron emission, in which a positron, or the antiparticle of an electron, is emitted. X-rays, a form of light, can also be emitted, as well as gamma, another form of light, emitted. The masses of atoms and the percent abundances of isotopes of elements are measured using mass spectrometry, a technique that separates particles according to their mass. In a mass spectrometer, the atoms whose mass is to be measured is injected into the instrument and vaporized. The vaporized atoms are ionized by an electron beam. The electrons in the beam collide with the atoms, removing electrons and creating positively charged ions. The ions are then accelerated into a magnetic field. When ions drift through a magnetic field, they experience a force that bends their trajectory. The amount of bending depends upon the mass of the ions. The trajectories of lighter ions are bent more than those of heavier ones. In the right side of the spectrometer, you can see 3 different paths, each corresponding to ions of different mass. Finally, the ions strike a detector and produce an electrical signal that is recorded. The result is the separation of the ions according to their mass, producing a mass spectrum such as the one provided in the lower left below. The position of each peak on the x-axis indicates the mass of the isotope that was ionized, and the intensity, indicated by the height of the peak, indicates the relative abundance of that isotope. We learn that because of isotopes, the atoms of a given element often have different masses. So we can calculate an average mass, called the atomic mass, for each element. The atomic mass of each element is listed directly beneath the element symbol in the periodic table and represents the weighted average mass of the isotopes that compose that element, weighted according to the natural abundance of each isotope. For example, the periodic table lists the atomic mass of neon as 20.10 AMU. Naturally occurring neon consists of 90.9% neon-20 atoms, mass of 19.92 AMU, 0.3% neon-21 atoms, mass of 20.99 AMU, and 8.8% neon-22 atoms, mass of 21.99 AMU. We can calculate the total atomic mass of neon by taking 0.909 times 19.92 AMU plus 0.003 times 20.99 AMU plus 0.088 times 21.99 AMU. This would be equal to 20.10 AMU. Notice that the atomic mass of neon is closer to 20 than to 21 or 22. Naturally occurring neon contains more neon-20 atoms than neon-21 or neon-22 atoms. So the weighted average mass of neon is closer to 20 AMU than to 21 or 22 AMU. The essential concepts for this video are as follows. Be sure to understand atomic number, mass number, and the weighted atomic mass average. Till next time when we consider the mysteries of the absolute, Crip.